Hello, thank you very much for being here with us, and I hope that you and your family are well. My name is Juan Escobar, and I work as senior security consultant. I'm in Chile at the moment, a land of excellent wine and also a country of many earthquakes. We are a pioneering Swiss company and source of constant innovation in the cybersecurity landscape, with 20 years of experience in almost all sectors of the industry and with a presence in various regions of the world. This talk is based on our experience in the field of security audits, incident response, as well as in the research of new vulnerabilities and how they are applied in the ICS KillChain. As a small introduction, ICS are devices that generally operate in critical infrastructures. These are not well known since they operate in different environments than the companies that have regular information technologies. Also, many incidents involving ICS devices and the OT environment have had very important geopolitical connotations, which has changed the world related to the vulnerabilities existing in them, which has led governments to take measures that classify them as a critical element of the nation. As many know, today we are in what is called Industry 4.0, which is characterized by broad interconnectivity, data collection, analysis, and communication, which result in the optimization of the flow and quality of the process. Although the benefits are many, this convergence between the IT and OT worlds increases the attack surface and as well as the amount of new control to implement. Based on this premise is that in the 90s, Theodore J. Williams, along with members of the Purdue University Consortium, developed the Purdue Enterprise Reference Architecture as a model for enterprise architectures, where the Purdue model defines the different levels of critical infrastructure that are used in production lines and the way to secure them. But as we know, in reality it is very difficult to implement, maintain, and monitor all cybersecurity systems. We must remember that not all the companies are the same, therefore the security mechanism and architectures are different. But at the base, all the activities to be carried out by an attacker will almost always be the same. And that's why Michael Asante and Robert Lee adapted the cyber KillChain model created by Lockheed Martin to the ICS world to understand, visualize, and organize steps required for an adversary to reach their goal. So, the ICS cyber KillChain consists of two phases. The first one is intrusion, which consists in the intrusion preparation and execution, also known as IT. And the second one is attack, ICS attack, and development and execution, also known as OT. So let's see what these steps are. For the stage 1, the first one is reconnaissance. So reconnaissance is an activity to obtain information about something through observation or other detection methods. This activity is divided into two phases. For example, passive and active. Well, passive is in charge of researching for the information available in public source, and the active interact directly with the target for the collection of this information. Okay, let's continue. First, let's define our target and the attacker. In this case, the target is a nuclear power plant called Macros, and the attackers will be a group called APT666. If we search for this nuclear plant in Google, we have a result, and we can see that this plant is located in Switzerland and also has other energy generation project. Continuing with the phase of recognizing, we do search in Shodan and Sumai, where there is probably not much information, which should always be the case. In LinkedIn, we find one profile related to the company and not much else in internet. It is when the attackers carry out an active reconnaissance. Obviously, both activity can be carried out in parallel. So let's start with an active reconnaissance. As we know, the plant is located in Switzerland, right? So we proceed to scan the entire country, looking for any reference to the company. One of the protocol consulted is SNMP, since although there are not many vulnerabilities for it, I think it provides a lot of important information to carry out an attack. So for this, I developed this tool called Meliodas, and this is an SNMP parser. So it takes some database name to save the results, and a community that usually is public or private, and a file name with the IP address that I want to scan. So in the result of the tool, we can see the IP address, the host name, the version name of the device, and also the day. So if we search for a string that has the name of the company Macros in the result, we can actually see that there is an IP address related to the company. So now we will see what information this device can give us. So for this, we will use a different tool. As we see, it gives us enough information. So now we know that someone is connected to this. We could assume that this is someone who is a system administrator, right? So let's see what we find in this IP. So we are launching a quick scan to see what ports are open on this IP that has connected to 22 port, and we can see that has port 80 open. right? So we access through the browser. Let's see what we can find, right? Okay, so we find a DryTech login website, right? So with a little more research and investigation, we see that what type of device it is and which part of the world IP address is assigned. So it's in the United States, and it has no vulnerabilities known. So a summary of the first step, we have one LinkedIn account, one website, one Linux server, one SMP service, one interesting IP, and one internet border device with no vulnerabilities. So now we are done with planning reconnaissance step, and we can move forward to preparation, which contains weaponization and targeting. This can be one or the other, or we can do both, but it's not required. This basically is to prepare the tools according to the identified objective. In this case, we will use two vectors. Vector 1 is social engineering, and vector 2 is infrastructure. Will consist on attack this DryTech router. Our goal for the social engineering vector is send a malicious link to the victim via a LinkedIn message, and the victim visits the malicious website, and using a browser exploit we can control her computer. And our excuse for this will be an interview for a magazine specialized in cybersecurity issues in industrial environments. So for vector 1, we create a fake profile of the journalist in LinkedIn, Luisa Lancaster, journalist focused on critical infrastructure, ICS, so seems legit, right? Also, we code a website for the magazines, SCADA-wired, and we have our exploit ready to be activated when the victim visits the website. So our plan for the vector 2 is also similar to the previous one. We want to redirect all the traffic to a malicious site, use a browser exploit deploy in the website, and install a command and control tool for remote access to the victim. But since we don't know who is behind this device, we need to hack the DryTech router in order to find some remote code execution or login bypass to change the DNS server. As we do not have the credentials and there is no vulnerabilities for this device, we need to find some vulnerabilities, right? So normally in this type of device, command injections to the fields of the web application is very common, and that we must identify the parameters where we are going to inject. So we fill some fake data, and with the browser console we can actually see the parameters. Okay, so these are the parameters: keypad and login user, login password, for captcha. So we identify 6 parameters, and with this information we proceed to create a fuzzer which will be in charge of injecting commas into the previously identified parameters and concatenate the command that user input. So each payload is going to inject a list of commands to be executed on the target. And also we print which is the payload, the status code, and response for headers and body. So we can start with the action field, and this will send all the command injection payloads to this field. So we can see that we have the payload number, status code, the response headers, and the response body. So what we are going to search here is, for example, some status code different for 200, right? For this field, the action field, I don't see like any status code different from this one. So we can try the next one parameter, which is key user, I think. No, it's keypad. So keypad. So in this case, we identify some error status code, right? And we identify some interesting body response, right? So the payload that we sent to the device was ID command between semicolons, and the device responds with the user that is running in the system, which is root. We can say that the vulnerable parameter is keypad, right? So now we can proceed to write an exploit in order to automate the queries. And as we are root, we can consult the password file and try to crack the hash. So as a root user, also we could modify the content of the file. So we launch hashcat and get the password, and now we can proceed to test it and look where the configuration for the DNS is located. Okay, so back to the stage 1 summary. The planning phase are done, the preparation phase are done, so we can now move to the next phase. So in this step there are 3 phases. First one is cyber intrusion, where you try to gain access to a network or system. The management and enablement phase, where a persistent communication is established, a figure of command and control, for example, And finally, the sustainment, entrachment, development, and execution phase, where different activities are carried out that will help to fulfill the goals of the attackers. In this step, the three phases mentioned above can be automated. For this talk, we will use Metasploit to summarize the phases. So first we will send the message to the victim and wait for she to enter into the page. But first we need to activate our exploit. We can do this removing the command line, save the change, and now if we change to the victim machine, so if the victim click on the link or just Google it, the exploit will be executed. So now if I change to my Metasploit console, I can see that I already have access to her computer. I got some credentials, right, with Mimikatz, and now I'm searching for useful information in like some common extension like OVPN, right? And now I can see that I found one result. So macros VPN, maybe interesting, right? Also I can search for keep as file station, right? So, and I found another result for this extension file work, and also Microsoft Excel files. So now we will continue with the second vector 2, and we proceed with the change of the DNS server on this target. In order to do this, we need to run DNS server on the attacker machine, and also redirect all the traffic from the beginning to our malicious website. So now that the fake DNS server are running, we can go to the Draytech device, log in with the administration password that we got with the remote code execution. So we can see that the default DNS server is Google IP. So we change with the attacker DNS server. Apply the change. So we can change to the other victim machine and see which DNS server he has configured. He already have the fake DNS server that we just run. This means that any request made in this browser, in the victim browser, will be redirected to the malicious website. So he can ask, for example, for Gmail website, and the fake DNS server should redirect the victim to our malicious website. So if I change to the Meterpreter section, I have a second Meterpreter section, right? Now we have the Windows user and password for the victim, for Jason, right? And we are basically doing the same that we did before with Lisa. So it's important to know that this process can be automated to perform more file shares, Excel files with information on the infrastructure, VPN connection, password managers, etc. So as we can see, this computer apparently belongs to an external technical that manages the IT area of the plant and connects remotely to manage it. This including VPN, for example, Berlin power generator, oil is company. We can also take a screenshot from the computer of the victim. Also, we can download the password manager and try to run a keylogger to extract the password for key pass, right? Search and look at the sensitive files, and all this process can be also done with the user Lisa, right? The operator user. So, as a summary, in this stage 1, we obtain the information and the sufficient means to access the infrastructure of the plant without the need to carry out other activities that could attract attention. Here ends stage 1, where part of the information obtained will be useful to complete stage 2. As the IT intrusion part is very similar to stage 1, in the stage 2 we will focus on the ICS devices. Continuing with the ICS cyber kill chain, but this is a second stage, attack development and tuning. So in the development phase, the attacking group tries to create a new offensive capability using the information of the previous stage, like stage 1. This is possible because the attackers have discovered documents with a list of devices, and in this case we can see PLC from Schneider Electric using Modbus protocol. First, it's necessary to understand the protocol. Lucky for us, this protocol is very simple. Without going into more details, the first 7 bytes of the packet, the one in red, respond to fields of the header. Continue with 1 byte reserved to declare a function. This can be between 1 and 127 in hexadecimal notation. So the following table here shows some common Modbus functions, right? For example, this is a very common function, read device identification. In the function code is 43. As you can see, the request is very simple. This one, for example, is a valid request using function 1. Function 1 means read coils. If the request is valid, the response will keep the function field with the same value. So, for example, you can see here and here. But what happens when the request is not valid? For example, contains an error. In this case, the answer will return 2 bytes reserved for 2 types of exceptions: exception function code and exception code. The first exception function code is equal to the total sum of the value or number of the function used plus 80 in hexadecimal notation. Since function code is 1, the exception function code value is 81. And the second exception, the exception code, is represented by a numerical value that will depend on the following flow. If a request can pass the first condition, the function is valid. In other words, if the exception code is different from 1, the function is valid. Based on the error messages, it is possible to determine the existence of the implemented function, and this is very useful for build-better attacks. It should be considered that an enabled Modbus function is always a possible attack vector. With this knowledge, it is possible to build a tool that can list the implemented functions. The tool sends valid module frames, always trying to force error messages and lists all the possible functions, their attack vectors. To continue our simulation, we, the attackers, will focus on functions 43, read device identification, and function 19, UMAS, both discovered with our new enumeration tool. What is that function 43? In summary, if this function is implemented, it will provide information about the device. Here are some first tests with the script using function 43, and we can see some information about the project. For example, in here. The other interesting function of Schneider Electric device is 19. Among the many functionalities available at the moment, we are interested in the following three: start, stop, and read memory block. For the final attack, we look for a request that can easily generate a stop on the target devices, for which in our controlled environment, request has been sent to our PLC using only function 19, but with random data. The intention is to generate denial of service, or DOS. Finally, it was possible to get a denial of services by sending two null bytes. A tool is developed for this attack, we call Modbus Killer. The next step for stage 2 is validation. In the validation phase, the aim is to certify the new capabilities or development in a controlled environment with a specific hardware. All tests has been performed in a lab environment such as the one shown below. As it was possible to observe, the resulting denial of service turns off all the functionalities of the PLC and also disconnects it from the network, forcing you to restart it physically. Successful exploitation of this vulnerability makes the device unresponsive, requiring a physical reset of the PLC. In the following demo, a denial of service is evidenced with the Modbus Killer tool. And the final phase is called ICS attack. This phase corresponds to the deployment of the new offensive capacity 0-day. And this is ICS Cyber KillChain complete. And just in case, we already report these vulnerabilities discovered, and they are already have their security update. You can see some recommendations overview. So thank you very much for your attention, and please visit us in our ICS blog at dreamlab.net or in our GitHub repositories, Industrial Army. We have all the tools that we present in this talk in our GitHub repository. If you have any doubt or want more information about this topic, you can contact us at LinkedIn. So thank you.